So in the last video, we talked about two types of factoring polynomials. Now we want to move on to the third type, what I like to call as the third type. So I will start with an example. Let's call this example 3 because we did 1 and 2 in the previous video. So example 3, I started with binomial, then we move on to a trinomial. Now I want to talk about when we have 4 terms. So if we have a polynomial function like x cubes plus 3x squared minus 4x minus 12. So if we want to factor this polynomial, the very first thing again we'll go back to is trying to look for the greatest common factor here. Again, if you compare all these quantities, the greatest common factor is only 1. So 1 is not going to help us much, so we have to figure out some other method. Again, it is not a trinomial, it's not 3 terms. If it were 3 terms, then we could actually go back and see if the leading coefficient is 1 and then try our other method that we learned in the previous video. So none of those two methods actually directly work here. There's another method that we can use here which is called as the method of grouping. So that is method number 3, which is called the method of grouping. It's a very simple and straightforward method. What you have to do for this method, you have to, as the word grouping suggests, you just have to group 2 quantities together. Well, sometimes we may have to group more than 2 quantities here, but for 4 terms, with the grouping method, we only combine or we only group 2 terms at a time. So when you group these 2 and these 2, in this example, they are already written out in a nice form so that we can easily group the first 2 and second 2. Sometimes we may have to do some rearrangement before we can actually group them. In this case, everything is written out clearly. So if we group first 2 and second 2, then we go back to the basics of trying to see if there's a greatest common factor. So greatest common factor is like the heart of grouping or the heart of factoring. So once we see that these two, once we compare these two, we can easily see that the greatest common factor between these two is x squared. Why is it x squared? Because x squared perfectly divides the first term as well as the second term and is the greatest common factor. Again, what do we do with the greatest common factor? We just take that outside and then we have to start drawing 2 parentheses as we did in the binomials, with the binomials when we had to just take out the greatest common factor and fill in the pieces inside the parentheses. Here when we take out an x squared, then you have to think, what would I multiply to x squared so that I get an x cubes? So I multiply x because x squared times x is x cubes, and then I have to multiply x squared times 3, which gives me 3x squared. So that takes care of the first 2 pieces. We have to do the exact same thing for the other 2 pieces. Look for the greatest common factor, take it outside and fill in the parentheses. This is my suggestion here, which really helps to simplify and write the factors. When you have a negative number in the beginning of the second term, we should always keep that negative. We should always keep that sign. So if there was a positive here, I would just keep that positive. Then I would compare these 2 terms, and comparing these 2 terms, we can see that 4 is the greatest common factor. It divides this quantity as well as the other quantity. So I'm going to write that 4, keeping that negative, which was already in the original polynomial function, and then I'm going to fill in the rest. 4 times x gives me 4x. Then I'm trying to get a negative 12, so I'm going to have a plus 3 because we know negative times positive is negative. So we have to be careful with the signs. Now once we are done with that first step, a quick check that we are on the right track is to see that this term in the parentheses and this term, the other term in the parentheses, have to match. If they are not matching, then there's 2 possible things that can happen. Either we cannot really factor them using the grouping method, or we have made some sign mistakes. So please make sure that you carefully distribute the negatives if there are any, so that these 2 things actually match. Once these 2 things match, we again go back to the same greatest common factor method. Now you can compare this term and this term. Comparing these 2 terms, you can again see that x plus 3 and x plus 3 is the common factor. And what do we do with that common factor? You just write that common factor out. Well, in this case, it's like a binomial, but it's still a common factor. So I just take that outside, and then what is left in the parentheses is this x squared term from the first quantity here. So I'm going to write that x squared. And from the second piece here, I have an minus 4. So we're almost done with the factoring, because remember the factoring, with factoring we want to write a polynomial function as a product of 2 or more. We have already been able to write this as a product of 2 quantities, but now I'm going to tell you about the fourth, and then there's actually the fifth method as well. So this, I didn't want to call this as a separate method, but it's like one of the methods that we have to use sometimes when we have a difference of squares. Because if you look at the second polynomial here, you can rewrite this as, well, the first one would be written as x plus 3. It's already a linear function. We don't want to change anything about it. But this quadratic function can be rewritten as x squared minus 2 squared, because 4 can be written as 2 squared. So whenever you have a difference of squares, so this is difference of squares. The difference of squares, this can be factored as x minus 2 and x plus 2. So this is our fourth method, which is called the difference of squares. It only works when we have a difference of 2 squares. So we can move on and write the final factors as x minus 2 and x plus 2. And that actually gives us 3 factors for this polynomial function. Are we always going to get 3 factors? Most of the time, yes, but if this was not a perfect square, let's say if this was a 5, then we don't really want to go ahead and try to write the factors for that piece, because it's not, in that case it's not a perfect square. This only works when these numbers here, this number here is a perfect square, like 4, 1, 9, 16, 81 and so on. So in this case, these are the steps. You start with grouping, then you do the greatest common factors. If there's a difference of squares, then you do use the difference of squares formula, and here we have the factors. Okay, so this is the third and fourth method, kind of. Well, I don't like to call this as a separate method, but this is also a part of this whole grouping process here. And now the last example will be based on a trinomial where the leading coefficient is different than 1.